Okay, thanks, John. Thanks very much, everyone. Thanks for joining us this afternoon. Thanks to the conference organisers. Thanks to Christopher Mallon, Mike Walls, Alex Cole, and Mick Hutchins. It's great to be back and to combine the two meetings. PVSAT was postponed last year, so great to be able to sort of pick up from where we left off last year. I'm going to talk today about some of the recent work we've done on copper zinc tin sulfide solar cells. But one of the messages I want to leave you with at the end is that some of these things, which are really kind of manufacturing insights in places, are highly transferable. And that's one of the things we want to focus on, transferable across PV technologies. So hopefully you'll have a good sense of that at the end. So for those of you that don't know me, I should say I'm at Northumbria University, which is in the northeast of England, in Newcastle. Let's just see if I can move this forward. There we go. So yeah, you may know where Newcastle is. So I'm sure most of you do, fondly known as the Toon. The picture on the left here is of my house and a recent PV installation which went on the roof there last month. These are sun power modules, and you can see the tiling which Martin referred to this morning. And it's a 3.25 kilowatt system which is made about just over 700 kilowatt hours in the, well, just less than 2 months that it's been installed. So good time of year to install it. Mike mentioned this morning in his figure, £823 per kilowatt. This was slightly more than that. So I think that was quite, quite a sort of let's say generous figure, but we're not far off that. The rule of thumb I use is £1,000 per kilowatt installed. Yeah, so that's something I didn't think I would see, but there it is on the roof of a house in Newcastle, which is great. So let me just move this on again. So overview of my talk. So it's two parts really. There's a kind of manufacturing part, which is how we make these solar cells, which are from nanoparticle ink, so slightly different technology to what we've heard of this morning, earlier this afternoon, and then a little bit later on, some of the selected physics of that manufacturing, including a novel experiment we did inside the TEM, and how we might make our devices a bit more sustainable. So the manufacturing part first. So this is how we make our copper zinc tin sulfide nanoparticle ink. We inject here metallic precursors into a hot surfactant, which is OLA, and we do the reaction at around 250 centigrade for around half an hour, and we're able to nucleate these nanoparticles, and which have the Kesterite phase. And interestingly, for this fabrication process, that phase, that crystal structure, is preserved throughout the manufacturing process or the fabrication process, and that's different to co-evaporation or sputtered Kesterite solar cells, or indeed SIGs as well. Then what we do is we suspend these nanoparticles in an ink, which you can see here, and we then spin coat. So the ink, I should say, the solvent is hexane thiol, and we spin coat these onto sort of molybdenum coated glass substrates as sort of standard, and then we end up with a thin film of nanoparticles. And then what we do is we convert these copper zinc tin sulfide nanoparticles, the thin film, to polycrystalline copper zinc tin sulfur selenide polycrystalline thin films by annealing them in a selenium-rich atmosphere at around 500 degrees C. So we can make these nice grains that are suitable for absorbing the incident light. We have a conventional thin film architecture and a substrate configuration, and we deposit our CDS on top of our photovoltaic absorber and finish in the usual way with zinc oxide TCO before putting contacts down, and then we can make solar cells like this on different substrates. This one is a molybdenum foil substrate. So that's our basic sort of fabrication process, if you like. What we find is using this spin coating deposition technique, it works rather well. We can make these kind of really compact nanocrystalline nanoparticle layers, and they can absorb the light. And we can build up these layers here in the right diagram by just repeated spin coating, and you can see the layers here indicated like that. So although it works well, one of the disadvantages is it's rather wasteful in terms of a process, and we can only make small samples. So a lot of the ink will fly off the spin coater into the edges of the crucible. The samples are rather small, and it takes quite a bit of time. So one of the things we've done recently is we've changed to slot die deposition, which with some success. So basically, what we've got on this side is a sort of couple of on this slide is a couple of one image and a sort of montage of images and a video. So here you've got the slot die head. Here you've got the photovoltaic absorber. So the slot die head is depositing the nanoparticle ink over this, in this case, sort of microscope glass slide, soda lime glass, to create this nice absorber, just like the spin coating case. And then in cross section, it looks nice too. And we can make this much more quickly and with much less wastage than with the spin coating technique. So that's great from a sustainability point of view, but also, we're also able to make larger samples, which is nice. So here's a video of the thing happening in action. So here you can see the slot die head being dragged over the substrate, and you get this really nice uniform absorber. I mentioned our device configuration. So we have our substrate. We coat that using sputtering with molybdenum. Then we do the process that I've just described via nanoparticle inks via slot die, and then annealing them in a selenium-rich atmosphere or selenizing before depositing the cadmium sulfide using chemical bath deposition in the usual way for the buffer layer, and then finally sputtering zinc oxide ITO and evaporation of metals on top. I don't cover that in this presentation, but actually we can also now print our contacts on top using silver inks. So that's something that we've been doing recently, and again, that works rather well. So we can, and again, I should say that one of the advantages is, you waste a lot less material when you do that, and you have interesting possibilities for rapidly reconfiguring the contact geometry and design, which opens up new possibilities. So we slot die coated our nanoparticle ink on 3 different substrates, so soda lime glass, Corning's willow glass, which is ultra thin, and on molybdenum foil. And the image there at the bottom shows you one of our foil substrates, which we coat directly via sputtering with a moly layer. So here's our performance from the slot die using these 3 different substrates. So on soda lime glass, we get around 7.7% efficiency, with reasonably good, sort of parameters. The VOC, of course, is the big problem in CZTS solar cells, and I think that's been a problem for quite a few years now. And that was, you'll remember in Martin's talk this morning, those 4 criteria. See if I can remember them: abundance, and non-toxic, stable, I had them written down here, and the last one, efficiency. So that's our problem with CZTS, but it is a reasonably good candidate for coupling with silicon, as he mentioned. Then on the flexible glass, on Corning's willow glass, we have around 5.4%, and on the foil we have around 4%. And of course, the soda lime glass is the only one with any intrinsic sodium doping. So I'll say a little bit more about that in a minute. So these are our sort of best devices from the slot die process. That's the average values of their performance, of their efficiency. It's repeatable. And the interesting thing there at the far right hand side of that graph is how the slot die process compares with the soda lime glass. So you can see a big improvement there in efficiency, and also over a larger area on a range of different substrates. So that process is working well for us at the moment, and we hope to develop that more in the future. One of the issues with these substrates I mentioned, like the foil, is that they don't have an intrinsic source of sodium doping. So this was a technique we came up with to introduce doping directly into our nanoparticle ink. So these are the dopants schematically included in the ink here. So we dissolved sodium fluoride powder directly in the ink. And when you do that, you get a nicer absorber in top view, and it is slightly thinner. And interestingly, one of the characteristics of this process, the nanoparticle ink process, is kind of an unconverted or unselenized layer, which is carbon rich at the back of the device, and that carbon coming from the surfactant in the process. And we're able to reduce that a little bit with this doping technique, and also we get a slightly thinner overall layer. So we get some kind of better conversion of the nanoparticles into grains. It's also challenging, I should say, to dissolve the sodium fluoride like this in the ink, and we're looking at other approaches to doing that. And of course, other groups have indeed done that, so we'll be looking at that as well. But this approach seemed to work quite well. I think the efficiency of these devices were, I think, up to 4.5%. These were spin coated, these ones we're looking at, and that's not bad at all compared to, I think the best nanoparticle ink, or the best flexible molyfoil CZTS devices, around 9 or 10%. That was a Nature Comms article a couple of years ago now. So there's our efficiencies. There's with and without the doping for a spin-coated device, and some of the parameters around the shunt resistance. Needs some. Well, the shunt resistance needs work. The EQE shows the effect of the doping, and if we want to quantify the doping, we used SIMS first of all to qualitatively check where the dopants are. So there you have the orange dashed line here. This is the sodium doped sample, and then so it tells you where your sodium is in the device, and we've got overall higher levels for the doped device as you'd expect. And then when you do the CV to look at the profile of the acceptors, you can see we can to some extent quantify this for the doped device. So that was really a simple kind of manufacturing compatible technique that we used to introduce dopants. We're also able to flex these cells. So the image on the right here shows the device in the flat state. This is in the curved state with a radius of curvature of about 6 centimeters. And we don't see really any big difference in efficiency, no degradation between flat and curved state. And then interestingly, when we cycle these in a loading or a fatigue type test, the devices hold up pretty well indeed. So we don't see any degradation as a result of that, of 100 cycles. So that's encouraging. So that was the kind of the manufacturing, what we're doing, and some of the applied stuff. This is a bit more about some of the physics, and this is an interesting experiment which we did in Singapore. And the picture here shows essentially this is what they call a nanoreactor. And inside the nanoreactor, we're able to put a single layer of our nanoparticles, then evaporate this red layer, a very thin layer of selenium on top of that, and then inside the TEM, study the evolution of these nanoparticles in terms of crystal structure and morphology in real time from this over this temperature range, 26 to 700 degrees C. And that was, I think that was a very new experiment and really interesting and fun to do. So essentially, this is what we see. So we see, in the kind of range 26 to 450 degrees, these are extracted diffraction patterns. We see the system evolving from the CZTS, which is the sulfur system, these nanoparticles, to CZTSE nanoparticles. So we replace nearly all the sulfur with the selenium, and that causes some lattice distortion, and we end up with this kind of thing, at 450. And these lattice constants are consistent with what we see from our XRD data as well. So that's kind of nice. And then here's, just again, the kind of another representation of that really. You've got this kesterite structure of these nanoparticles, which starts off at room temperature, and, it stays in that phase as you incorporate the selenium. So at 450, you have CZTSE nanoparticles. Something interesting then happens around 500 degrees. These sort of rings that you have here start becoming these diffraction rings become spots. And so we see an improvement in the crystallinity. And we also see some slight change. The 2-on-1 reflection appears now, which might be indicative of increased ordering of the system. And we see some grain growth in the TEM images, and I'll show you that in the next slide. So this is a region of the nanoparticles. What you'll see when I click play is you'll see the formation of a grain around the red arrow here in this temperature range 490 to 500 degrees C. So let's see if that works. So there's the evolution of that grain just growing from the nanoparticles. And interestingly, when you if you watch inside this dashed oval area as well, you see sort of consumption, if you like, of these nanoparticles while this grain grows. So you kind of see that area getting reduced there. So it's a kind of Ostwald ripening type process. And what we were able to do was transfer that sort of protocol that we determined from the TEM to an industrially similar process, not an industrial process, but a macroscopic process. And we're able to use the insights to increase our VOC in the device by around a third, which was great. So really sort of good sort of crossing of scales there to obtain some, from the nanometer scale to the device scale. One of the things that we want to do is try and we've heard a bit about this as well today, is look at the buffer layer and how do we replace cadmium in these devices. And we've done some simulations looking at cadmium sulfide versus indium sulfide, and indium sulfide has a slightly more favorable conduction band offset, which should help with, there you go, there you can see it there, which should help with the open circuit voltage. And when you do the kind of drift diffusion modeling, you can see that in theory the indium sulfide system should work quite well, not just from the band alignment but also from the JV data. And so we set about trying to recreate this experimentally, and here's our conventional system. So there's a device which is around 7% efficient with light and dark IVs. There's its structure, and here's the cadmium sulfide. And then the parameters are in the yellow box on the right. And then when you replace that with, first of all, a dual buffer layer, so you have a very thin layer of cadmium sulfide and a much thicker layer of indium sulfide, we get to 7.8%. And in fact, if you take the size of the contacts into effect, that goes over 8%, that figure. So that's quite good. When we replace with just indium sulfide alone, we're only around 5.4%. So there's good progress there too, but work to do at that interface. And of course in CZTS, that interface and the defects, that's what it's all about. So that's encouraging, and that's what we'll be able to incorporate a lot of this into that manufacturing knowledge and insights that I presented in the first part of the talk. So I want to take that point to wrap up. We've done a multi-scale investigation of the PV absorber fabrication and of our device fabrication, and we have an increasing focus on the manufacturing research, and in particular on the manufacturing research that will enable different materials to be deployed in PV devices that are unusual and innovative, so unconventional types of implementation, including product integration. And I think that is something that could be looked at. I found Martin's talk very inspiring this morning. I'm sometimes a little bit depressed about climate change, but I found it very inspiring this morning, the rate of deployment of PV. But we really need big, grand thinking on this, and I think that extends beyond large-scale solar farms. I think and if we want to integrate it with other products, we're going to need manufacturing innovations and new thinking in that regard. So I just wanted to acknowledge the work of our team, who have had an exceptional year, as have many of you on the call, all of you on the call. It's been difficult at times, and the pandemic has affected everybody in very different ways. I've seen that from the people I manage, and all of these people and the other people that we work with have responded magnificently to that and done really well. I'd also like to just acknowledge the funders, UKRI. Some of these students are CDT students in Renew. If you want to learn more about our research, you can follow us on Twitter. One thing I also didn't say as well at the start is just a note to the organisers to say that I think the introduction of the Childcare Fund is absolutely fantastic, and really like to commend you for doing that. I think that's the sort of thing that we need to be doing in future. So I really think that's trailblazing and pioneering. So, you know, congratulations on that front. And with that, I'll stop there. Thank you.